Alright, now we should talk about transition metals. So we remember that a transition metal is a metal that can have multiple different charges or oxidation states. So this gets a little bit more tricky because we need to be able to know what the charge of the metal is before we can figure out the chemical formula or its name. So we need to be able to identify the metal charge before writing the formula. We can still do the crisscross, and we can still write out the formula and simplify. So pretty much the same steps. So here we have an example. If we were using iron with, if it showed parentheses with 3 Roman numeral marks, that's saying that this iron has a charge of positive 3, because our metals are always going to be positive, and this is telling you what that charge will be. So that's Fe3 plus. And then if we wanted to react it with oxygen to make a compound, oxygen has a -2 charge. So just like before, we can crisscross and we end up with Fe2, that 2 came from the oxygen, O3, that 3 came from the iron. Another way that you can do this is try to figure out what can allow 3 and 2 to cancel each other out. So 2, if we multiply it by 3, goes up to -6. And 3, if we multiply it by 2, goes up to +6. And then 6 and -6 would cancel each other out, and we'd have a neutral compound. So that's just the other way that you can think about writing out the chemical formula. So then if we were to use iron 2, this is the other type of iron we could come into contact with. And let's say we wanted it to be reacted with chlorine. Okay, so that means we'd have Fe2 plus, and chlorine is a -1. So if we crisscross these charges, we get Fe, and that 1 would be here, Cl2. So this is the formula for that. Okay, now I haven't shown you what it would mean to simplify, so actually let me just sneak that in right here. If we had iron Fe2 plus with oxygen, which is that 2 minus, if we were to crisscross, we would end up getting Fe2O2. That is not okay because it's not the most simplified version of this compound. If we divide both of these by 2, we'd get down to just FeO, which is the most simplified version. It's still the same ratio of elements, but now it's simplified down. Okay. So for naming, the metal is going to go first. It keeps its name, but add Roman numeral in parentheses. Okay, so that Roman numeral is going to tell us the charge of the metal. The non-metal, it still ends in "-ide", and it goes second. Okay, so if we wanted to name the first example we did, this is going to be iron oxide, but we need to show the Roman numeral for the charge. So the charge is 3 of our iron, if you recall. So we're going to write iron 3 oxide. Okay, so then we get to the next one. If we wanted to name this one, we would have iron 2 chloride, and that's because the charge of the iron is 2. And then this last one here, FeO, if we wanted to name it, it would be iron 2 oxide. So that's the difference between iron 2 oxide and iron 3 oxide is iron 3 oxide has this formula. It's got 2 irons and 3 oxygens, but iron 2 oxide only has 1 iron and 1 oxygen. Last, we're going to move to covalent compounds. So this might be a little bit more difficult to understand than some of the other stuff, but we're not really expecting you to understand how to draw a Lewis structure. We just want you to be familiar with them for naming the compounds and recognizing their chemical formulas. So a Lewis structure is a molecule drawn in 2 dimensions showing connections of bonds and lone pairs of electrons. I didn't really think about the definition for that ahead of time, but hopefully that will kind of explain itself once you see what it looks like. Okay, so for naming these covalent compounds, the first element only gets a prefix if there's more than one, but second element always a prefix. Okay, so prefix just means the thing you put on the beginning of the name. Alright, and our prefixes are mono, mono means 1, di, di means 2, tri, you could probably assume tri means 3, tetra means 4, penta, like a pentagon, means 5, hexa means 6, hepta means 7, octa means 8, and so on. We could keep going with this. Okay, but for the covalent compounds, we're going to be using two nonmetals. So let's say that our two nonmetals we wanted to use were carbon and hydrogen. And let's just say I told you that we're going to need 4 hydrogens and 1 carbon to make this compound. Okay, now the first thing you need to do is add up the valence electrons. Okay, so carbon has 4 valence electrons, hydrogen has 1, but there are 4 hydrogens. So that means altogether we have 8 valence electrons. Okay, that's our first step. Our second step is to connect all atoms. Okay, and we're going to do this so that the least electronegative is in the center for most covalent molecules. But in this case, it looks like that would mean hydrogen would go in the middle, but carbon, if carbon is an option, it's pretty much always going to go in the middle. Okay, so I'm going to put carbon in the middle. I'm going to put 4 hydrogens around it. Okay, and then we're going to connect them. And when we connect them, we draw this line. This line represents a covalent bond between hydrogen and carbon. Okay. Next, you need to subtract 2 electrons from total for each bond. Okay, so that means I have 1, 2, 3, 4 bonds. So if I want to subtract 2 per bond, that means I need to subtract 8 electrons. And I only had 8 to begin with. So 8 minus 8 brings me down to 0. So now I've used all my valence electrons that I had to go around. But the thing you need to make sure is check that valence is filled for each atom involved. So carbon needs to have 8 valence electrons in its outer energy level to be filled up. And if we look around, it's got 4 bonds, and each of those bonds has 2 electrons. So carbon has 8 valence electrons surrounding it. So it is full. Our hydrogens, however, are on the first energy level, and the first energy level fills up with only 2 electrons. So when hydrogen has 1 bond going to it, that's enough for it. It is filled with 2. Okay, so that's true of this hydrogen. That's also true of this one and this one and this one. They each have 1 bond going to them. So just in general, carbon will make 4 bonds. And in general, hydrogen will make one bond. That's kind of a little shortcut there. We could have gotten to this structure. So basically just C with the 4 lines with the H's around it. This is the Lewis structure of CH4. So if we wanted to write the formula, this is the structure, specifically the Lewis structure. If we wanted to write the formula, it would be written out as CH4. And then if we wanted to write the name, remember that the first element will only get a prefix if there's more than one of them. So carbon, we don't have more than one carbon, so it's not going to get a prefix. The second one is always going to get a prefix, and that prefix tells you how many of them there are. So we're just going to write carbon, and then we need a prefix for hydrogen. There are 4 hydrogens, and the prefix that means 4 is tetra. So we're going to write carbon tetrahydride. So it's going to end in that "ide" ending, just like our ionic compounds did. And that's it for naming our covalent compounds. Now, we'll have to see a lot more examples of covalents, but this is a good little introduction for us. All right, that's it. Thank you.